In today's lesson, we're going to be solving systems of equations using matrices. So our objectives are that you're going to be able to solve system of equations first by using substitution, and then you're going to solve systems of equations by using inverse matrices. So we're starting out by looking at solving by substitution because that's what we've done in the past. And for your activator, that's what I anticipated that you were going to do, that you were going to solve that two variable system by using substitution, solving for one variable, then substituting for the other. In the instructional focus today, we're going to once again take a look at that, solving a system with substitution, but then we're going to learn how we can use inverse matrices to really streamline and simplify the process. Going back to the activator, I likely would have approached this problem by starting out by solving for, say, y. I would have said, negative y is equal to 10 minus 2x by subtracting 2x from both sides. Divide by negative 1. That way you get y is equal to, in this case, it's going to be 2x minus 10. All right. I would then take that value for y and I would substitute it into the other equation. So I would have 3x plus 2 times 2x minus 10 is equal to 1. This would be 3x plus 4x minus 20 equals 1. So 7x is going to equal 21, so x is going to equal 3. We then plug that back in. You get 2 times 3 minus y equals 10. 6 minus y is 10. Subtract 6 from both sides, you get negative y equals 4. Therefore, y is equal to negative 4. So we're able to solve y is negative 4, x is 3. We were able to solve the system, and I did it this way using substitution. Now, that's one way in which we can solve systems of equations. And it's a perfectly valid way. It's what we learned how to do back in algebra. But now we're going to find some much more efficient ways to do it in this lesson. All right, so let's start out solving by substitution. Once again, if we want to solve something by substitution, we're going to use what we know to solve for other variables. So in this particular problem that we have on the screen, this example, we're given the value of z. Z is 3. We can substitute that back into the second equation, y minus 2 times 3 equals negative 7. Y minus 6 equals negative 7, therefore y equals negative 1. We're now going to take z equals 3 and y equals negative 1, and we're going to substitute into the first equation. X minus 2 times negative 1 plus z plus 3 equals 7. X plus 2 plus 3 equals 7, therefore x has to equal 2. So you should get x is 2, y is negative 1, z is 3. Once again, that's how we solve using substitution. And that's what this breakdown here tells you. It's the exact same thing as what I just did. Kind of just puts it in a format and explains it how a textbook would, but the process is exactly what I said. It's just taking that variable that we know, substituting it into the other equations, finding out a new piece of information, substituting that in, and eventually determining the solution to the system. So I've discussed a couple times already that we're going to learn to solve systems using matrices. So this is essentially how this is going to work. All right. And we could read this theorem as it's written. It might be a little confusing if I just read straight through it. You can read it in your own time. But essentially what it's saying is if we take, for example, and we're going to use the system that's on the screen right here. We have a system that we're going to solve. If we take a matrix and we call it A, all right, so this is matrix A, and all it's going to be are the coefficients in front of X, the coefficient in front of Y, the coefficient in front of X, the coefficient in front of Y. So we have a matrix that's all it is the coefficients, right? If I were to take that and multiply that times the x and the y, a matrix, right, that has x and y as its elements, that should yield what's on the right-hand side, 0, 5, right? Because if I were to take 3x plus a negative 2y, it would give me 0, right? This is just how matrix multiplication works. So if I take the coefficients times the variables, it will yield the overall output. Well, what's a great thing about this, and now your xy is going to be the matrix that we call X, and the resultant matrix over here we're going to call B. Well, if we remember the way inverse matrices work, I could actually take the inverse of A, multiply it times matrix B, the results, and that will give me xy. That'll give me the result of my variables. So essentially, all I need to do is take the inverse of A. So if I plug in A as that matrix and I plug in B as the other, all we have to do is take the inverse of A times B, and it will tell me what the values are for x and y. So I'm going to pull up my calculator. I'm going to go into my matrices. I'm going to go to edit. All right, and the first matrix, 2 by 2, it's got 3, -2, -1, 1. That's matrix A. Matrix B, all right, and we're going to edit that as well. Matrix B consists of just 0, 5, right? That's my resultant matrix. And now all I'm going to do is I'm going to go into matrix. I'm going to say A, inverse, times, go back into matrices, choose B, and I'm going to multiply those together, and I get 10, 15. I get x equals 10, y equals 15. And if I plug in those values, 3 times 10 minus 2 times 15, all right, that would be 30 minus 30, it would give me 0. Well, that checked out for the first one. Negative x, -10 plus 15, that gives me 5. It checks out for the second one. So it is the solution to this particular system. So in order to solve a system of equations, all we need to do is the inverse of the coefficient matrix times what's on the right-hand side of the equal sign will give me my set of variables. All right? That's a simple way to solve a system using matrices, and it makes solving a system super easy compared to the process of substituting and going through quite a bit of work trying to solve for the different variables one by one. The process for that example is right here, written out a little bit more cleanly, so it's not just my messy handwriting. But here's that solution. You can read through it if you would like, but it kind of breaks it down the same way. Matrix A is the coefficients, matrix X is the variables, and B is the result on the right-hand side of the equal sign. And so to find X, we just do inverse of A times B. So I wanted to jump back to an earlier problem where we could still use this exact same method. Now, if we take a look at this earlier example where we just substituted the value for z in, etc., we solved by substitution. If you were to get this particular problem and said, hey, can you solve this using inverse matrices? You might look at this and say, well, no, because I can't really make a matrix that represents the coefficients here. Well, in reality, you can. All right, that matrix A would be a 3 by 3 matrix of the coefficient. In the first equation, we have 1 for x, -2 for y, 1 for z. In the second one, I don't have an x. What that means is the value would be 0. For y, it would be 1, and for z, it would be -2. In the last one, we would have 0, 0, 1. Our matrix for B would be the result on the right-hand side, which is 7, -7, 3. And that would equal, when we multiply them, x, y, z, so long as I take the inverse of A, right? So inverse of A times B. So it's not that multiplying the first matrix times the second. We would have to take this matrice's inverse. So the inverse of A times B would yield x, y, and z. So let's go ahead and do that real quickly. I'm going to pull out my calculator. I'm going to go matrix. Nope, got to turn it on. I'm going to go into my matrix. I'm going to go to matrix A. I'm going to edit it. It needs to be a 3 by 3. Our coefficients were 1, -2, 1, 0, 1, -2, and 0, 0, 1. All right, for matrix B, this is going to be a, I needed to edit it. We go to edit matrix B. It's now a 3 by 1 with 7, -7, and 3. Then we're just going to basically do what we did before. We're going to say matrix A inverse times matrix B. We hit enter, we get 2, negative 1, 3, which is exactly what we got as our solution when we did this problem earlier in the lesson. So just note, if you don't have an x, y, or z, if you don't have one of the variables, that's okay. Just put 0 as its coefficient and it will still work. Now here's another system. The coefficient matrix 3, negative 3, 6, 1, negative 3, 10, negative 1, 3, negative 5, the resultant 20, 40, 30. All right. We can go ahead, we set it up the same way. We multiply the inverse of a times b, and it's going to tell us the answers for the values of x, y, and z respectively. One of the things that's important to note is that if we go ahead and find the determinant of a, right? Remember, if it's not 0, that means an inverse exists. If the determinant of a is 0, what that would indicate is that there's no solution to the system. So in earlier math classes that you've taken back in algebra 2, if you were trying to solve a system, there were times when there was no solution. Well, in the instances where there are no solutions, we would find that the determinant would equal 0, meaning there would be no inverse of a, so we would not be able to find a solution. So now we can look at some applications of solving with inverse matrices. So any 3 non-collinear points with distinct x coordinates determine exactly one second-degree polynomial. All right, and the graph of a second-degree polynomial is a parabola. All right, so if we wanted to fit a parabola to 3 points, all right, we would actually be able to use inverse matrices to help us in this. And this is something that you might be like, what? This is very different from what we've talked about so far. So let's just take a look at this example. So if we wanted to determine a, b, and c so that the points negative 1, 5, 2, negative 1, and 3, 13 are on the graph of f of x is equal to ax squared plus bx plus c. All right, and I want to be able to fit a parabola to those 3 points. All right, how might we go about doing this? Well, one of the things that we know, all right, is that in f of x, if I plug in negative 1, all right, I'm going to get the answer 5, right? Which is just basically saying if the x value was negative 1 in each of these, I would have a minus b plus c, it would give me 5. For f of 2, if I plug in a 2 for x, I would get 4a plus 2b plus c equals negative 1. If I plug in a 3 for x, I would get 9a plus 3b plus c is 13. Well, now all of a sudden I have a, b, c. This looks a lot more like the equations, the systems that we've been dealing with, because we no longer have squares, right? We're able to kind of remove the x value because we knew it for 3 points. So now I just want to know, well, what are a, b, and c, right? That's what we're trying to determine. What are a, b, and c? And so now I can create a coefficient matrix, 1, negative 1, 1, 4, 2, 1, 9, 3, 1, etc. As we can see here. I know that my x matrix, my variables, are just a, b, and c. And I know that my resultant matrix is 5, negative 1, 13. So now when I do inverse of a times b, I get 4, negative 6, negative 5, which means those are going to be the coefficients of my polynomial. All right, so I could actually take and write out, f of x equals 4x squared minus 6x minus 5, and I know that that polynomial will contain all 3 of those points. And if we were to graph it, that's what we would get here. So we actually can take this idea of solving linear systems and kind of use it in a different way to figure out the equations for nonlinear equations, which is a pretty neat application, and one that might not be so intuitive, but this just helps to show the power of having these systems of equations and the power of matrices, because we're able to very easily solve these systems using these inverse matrices. So in this lesson, we looked further into our exploration of matrices to solve 3 variable systems of equations. We focused on solving by using substitution, which helped us to transition into how we can use a matrix and technology, our calculator, for finding the inverse to quickly solve systems. So you should be able to solve 2 and 3 variable systems of equations using substitution, as well as by using inverse matrices.